Hi, this is John Reinecker, Technical Services Manager at Kermetico in Benicia, California, presenting another webinar in our series of monthly webinars. Today's subject is alloy coatings and their applications with HVAF and our convertible HVOF coatings. First, I think it's important to discuss the difference between our approach to creating coatings with our HVAF and convertible HVOF system as compared to traditional HVOF coatings. Here we have diagrams of various HVOF guns compared to our HVAF gun. And the big difference here is that our diagram is in color. This makes a big difference. No, I'm kidding. These diagrams are all size scaled, and what's important about them is we're showing where the powder is injected, and all the guns are aligned at the point of powder injection. So we can also gauge how far the powder travels through the nozzle before it's unrestrained. So first up we have the JP type gun. Has a combustion chamber. Liquid fuel and oxygen is added and it burns. Combustion every which way. Gets choked down through a narrow point here and then off into the nozzle. Powder is injected radially from two sides. I suspect the idea here is that the two impinging powder streams will cause the powder to be locked up in the center of the nozzle and head downstream with the gases that are accelerating it and heating it from this point. Interestingly, as the gases expand, they're cooling, but the temperature is so high to begin with, 3100 C, that it really doesn't matter. What I suspect here is that if there is any alignment differences in these two powder ports, powder is going to be going everywhere, and that leads to all kinds of problems, including nozzle sticking for the material. Next up, we have a Jetco type gun, and here, although the powder injection is axial, the combustion chamber is 90 degrees to the line of flight for the powder and the barrel. So do you think these gases, when they make this 90-degree turn, will not interfere with the powder stream? I find that very hard to believe. I think the powder stream is going to be disturbed, and the reason for the shorter nozzle here is because anything much longer would result in powder buildup on the inside of the nozzle. Here we have a DJ type gun. It has a nice tiny little combustion chamber with axial powder injection, and I think that's the nature of the story. A tiny combustion chamber with a short nozzle that doesn't give you much time for acceleration. And then enter our color diagram of our HVAF C or convertible gun. First up, you'll notice that we have a ceramic element here in the combustion chamber. Gases are delivered behind it, and they exit through literally hundreds, many hundreds of tiny itty-bitty holes. So the flame is spread out over the entire face of the combustion chamber, and they're very small. So combustion is taking place very close to the ceramic element, and by the time you get down to transitioning to the nozzle, combustion is complete. Now, what we're doing here is a little bit different in that along with our powder carried with nitrogen carrier gas, we're injecting a trickle of hydrogen, not for combustion, but for thermal conductivity. Hydrogen has the highest thermal conductivity of any gas, and we use that to more efficiently transfer the heat of the combustion gases in the combustion chamber to the stream of metal passing through it. And incidentally, hydrogen acts as a wonderful oxygen scavenger to prevent oxidation of the material as well. Fuel and air come into the combustion chamber either with or without oxygen, depending on what we're spraying. And that air is preheated by having cooled the combustion chamber first. So we're making maximum use of that heated air. And the transition to the nozzle is smooth, and the nozzle can be as long as it needs to be to achieve the desired velocity, which could be as high as the gas velocity. This all results in very different characteristics for our coatings. First, a difference in our gun, as we pointed out, besides being in color, is that it's much larger. So in the combustion chamber, we have plenty of time. Because of the large diameter, velocity through here is relatively slow, so we have plenty of time to gently heat the feedstock material at a lower temperature than any of these other approaches. This way we're not vaporizing anything, we're not overheating it, and making a lot of fumes. The temperature, as I already pointed out, is lower, so this helps us by not melting feedstock materials and dissolving oxygen into them, and by vaporizing them. And we achieve a higher velocity because we can have a nozzle that is as long as necessary to get to the velocity we need. And the secret here is the highest velocity is not necessarily the best velocity. The result of all of this is that we have very high spray rates, 60 pounds an hour for carbides plus 50 pounds an hour for metals. Oxidation is negligible because we're using it mostly in combustion, and we have the hydrogen to scavenge any leftover oxygen. Coating density is extremely high because of the high velocity of the spray stream. Hardness is high for the same reason, and we maintain ductility because we're not dissolving oxygen into the metal matrix, as that tends to make coatings brittle, and solid particles absorb oxygen at a rate about 1,000 times less than liquid particles. And we're not specifically not melting anything. We're heating it to near its liquid phase and converting kinetic to thermal energy on impact to deform the particle and create a bond. Here we have a chart of various materials that we spray, the applications that they work best in, and their advantages over traditional HVOF, and finally the guns that we spray those materials with. Now, the fact that you see, say for super stainless and 6AB, you don't see an AK-5 or an ID gun does not mean that it's not possible. It just means we haven't done it yet. So if you have an application for these materials that require one of the guns we haven't developed a coating for yet, we could be convinced to do that. Hastelloy C is very popular. We use that in a lot of refinery vessels, and I'll be talking more about that in a little bit. The coating is impermeable. We use it at 10 thousandths thickness to resist acid attack in pressure vessels. Low oxidation in the as-sprayed state, and as you can see, we spray that with every gun in our product line. Stainless steel 316 and the low carbon version is a corrosion-resistant stainless. It's sprayed gas tight with very low oxidation, and we spray that with everything except for our tiny ID gun. Super stainless, or Hogan's 350, is a corrosion and wear resistant material that falls in the 52 to 55 Rockwell C range, and it is also gas tight, very low oxidation in the as-sprayed coating, and it is very wear resistant as metal coatings go. And as you can see, we only use our larger guns to spray that so far. 6AB is a Hogan's product. It's a ferritic stainless, RC60-ish, very wear resistant, and a good alternative to electrolytic hard chrome. Applied coatings have low oxidation in the coating structure, and they are surprisingly tough as hard coatings go. And once again, this is limited to our larger guns, only because we've had no reason to spray it with our smaller guns. Stellite 6, pretty popular coating at the refineries, a wear-resistant hard stuff. We spray with low oxidation, and we achieve higher hardness and better ductility or toughness than the HVOF or plasma versions of the coating. And once again, we haven't found a reason to spray that with our smaller guns. Nickel chrome boron silicon is a wear and corrosion resistant coating. We get no nozzle clogging with it, and we spray that with our larger AK-7 gun and our low melting point material guns. And the nickel silicon coating, it's got a little boron in it, but not as a self-fluxing alloy. It's corrosion resistant hydrogen fluoride, which comes out of the chemical companies. We'll be talking about that a little bit later. It's a very dense and low stress coating. We can make it very thick, and we've used that in all our major OD guns. Here we have an interesting comparison of nickel chrome applied by an electric arc, a plasma gun, HVOF, DJ type, and our HVAF process. What has been studied vis-a-vis X-ray diffraction is the oxygen content in the original feedstock material as compared to that oxygen content in the finished coating or the as-sprayed coating. Electric arc was 0.02. It's a wire, so you'd expect the oxygen level to be very low. but the as-sprayed coating had 7% oxygen, and that shows up in the micrograph. Plasma started out with 0.05 oxygen content in the feedstock powder, only slightly higher than the arc sprayed coating, but the oxide level, the oxygen level in the as sprayed coating is only 3.8%, just slightly above half that of the arc gun coating, and that too is apparent from looking at the micrograph. Then we have a DJ coating, same type, HVOF, 0.06% oxygen in the powder, but only 1.9% in the coating. And again, that is apparent from looking at the comparison in the photomicrographs between plasma and HVOF. And finally, we have our HVAF coating. The feedstock oxygen was 0.06%, same as in the DJ. But the coating was only 2.8% oxygen. That's something on the order of, 8 times less almost than the HVOF coating? And that appears clear from looking at the photomicrograph. There's virtually none to be seen. Then there's the difference in oxidation resistance between an HVOF coating and our HVAF coating. This is a photomicrograph of an OF coating, HVOF, alloy 625, after a 700 degree Celsius test in air for 1,000 hours. You can see a number of things which are not desirable. You see substrate oxidation, you see oxidation between the particles in the coating, and you also see intergranular oxidation in the substrate. What a mess. That didn't protect anything. Here we have our version of the coating. Same thing, 700 degrees C, 1,000 hours. There's virtually no oxidation at the interface, very clean. No intergranular or interparticle oxidation in the structure of the coating. And most amazingly, you see a diffusion line. Now, if there was any serious oxidation at that interface, diffusion could not take place. So this is clearly a much better way to go for oxidation-resistant coatings. Here we have an interesting chart that compares the G65 results for our 8610-4 coating against a number of other materials we've sprayed and some materials we did not spray. So it's pretty straightforward. You can see all the various materials and they fall into line very much as expected. Look at Stellite 6. Not as wear resistant as you would think when you compare it to our 8610-4 coating. Fuse coating, 57 Rockwell C, is 28 cubic millimeters lost compared to our 1.2. But here's the real yardstick. 8610-4, 1.2 cubic millimeters lost. Electroplated hard chrome, 24.6. That's over 20 times the wear rate of our 8610-4 coating. And here's the secret. This work was done some time ago when the coating that we were spraying then was not as good as the one we're spraying today. So results would even be better today. Here's a photomicrograph of Hastelloy C. Shows you how clean the coating goes down. Nothing here to really say much about. I refer to our metallography largely as boring metallography because there isn't really much to talk about. That coating gets used on refinery vessels. This is an example of one. It's a heat exchanger shell. We've coated the ID with 10 thousandths of Hastelloy C to prevent attack from acid containing fluids, hydrochloric, sulfuric, naphthenic, carbonic. I mean, you name it, they got it. It's all bad. This coating works very well. It's protected the vessels. We have some now going on 5 years or slightly longer. And, you get an idea of the scale of this vessel by comparing it to a 5,000-pound fork truck. The thing is huge. Here's a coating of 316 stainless. This was sprayed without aluminum oxide grit, and we'll get into that in a minute. It had no nozzle clogging, had a HV 300 Vickers 360 hardness, very respectable for that alloy, and the porosity was less than 0.5%. That coating was used on a number of applications. In this particular case, it was for a gas compressor liner. This is nickel chrome boron silicon sprayed with an AK5. with no nozzle clogging. We got 730 out of it on a Vickers scale, and the porosity was less than 0.5%. Again, a very clean looking coating. Little junk at the interface, but nothing that causes any serious problems. And here we are spraying it on a Spectre roll in the glass industry. This is the nickel silicon boron application I was talking about earlier. We spray a lot of plug valves for Dow Chemical. They have a lot of hydrofluoric acid, and it just eats the nickel alive. Eventually, there's some mechanical processes going on, obviously, from the looks of things. But we spray them up, and when they're ground, they look brand spanking new. We do them in batches of a dozen sometimes, and they go into service, and we don't see them for a while. Here we're spraying a Stellite 6 overlay on top of a weld overlay of Stellite 6. This wearing was machined too small, and they needed more material on it, so we were able to do that. Spraying onto hard substrates is challenging for traditional thermal spray processes. Eventually we run into a problem, but at much higher hardnesses than traditional thermal spray. So spraying on top of Stellite 6 is no big deal. And as you can see, the as-sprayed texture is extremely fine. It requires less finishing allowance than traditional OF or plasma coatings. Now we're getting into the metal matrix composite coatings. We mix either silicon carbide or aluminum oxide with the metal feedstock powder, as we found that it improves the density of the coating, the quality of the coating in general. Ductility is maintained. The downside is it makes it a little hard to gauge the porosity in a micrograph, which is ad hoc method at best. We test with our gas permeability tester, and more information on that can be found on our website. The URL is right here. And we find that this makes for a much better coating. And interestingly enough, you would think that it would interfere with the machinability of the coating, but it does not. So we're literally spraying metal matrix composites. Makes for very good coatings. This one has less than 0.5% porosity, and it passed through a 712-hour salt spray test. Pretty impressive results. There's an application that was done by our customer in the Russian Federation. They're having a lot of problems with their electrical submersible pumps, ESPs. The outside of the housings are being eaten alive by the rough layers of shale and whatnot they're going through. So we were able to apply we did, and they did, a coating that we worked out together, a combination of 6AB directly onto the housing, followed by Super Stainless 350. And a combination of those two coatings made for a corrosion-resistant and wear-resistant coating that significantly improved the performance of the housings. And they're spraying somewhere between 10 and 15 tons a year at our customer in Russia of those two materials on these ESPs. We're talking about kilometers worth of ESP housings here. This is another moderately popular coating. It's molybdenum boride cobalt chrome. It's lubricious. It excuse me, it has reasonable thermal shock resistance. It's hard at around 1100 HV 300. Anti-stick properties are good, and it is inert in molten zinc and aluminum. So it has use in the steel mills and other applications that I'm not at liberty to discuss because of NDAs. Here we have an example of some very nice looking metallography that you would think would be absolutely wonderful in every regard. These happen to come out of an HVOF evaluation, and they both look great. Alloy 625, alloy C, perfect looking coatings until you start to look closer. Now, if you just magnify things, you don't see anything that looks ugly. But wait, what's that there? It looks like an indenter, doesn't it? Maybe we get a little, oh my, there we have it, cracks. This was a K1C evaluation. This otherwise gray looking coating was brittle. And here's another pretty picture that had the same kind of problem. Here we have the improvement that's gained by adding aluminum oxide to the coating. As you can see, it makes it difficult to gauge the porosity in the coating, but the density is much higher. Junk is removed by the blasting effect, And the blasting effect makes for much better intimacy between the particles that build up the coating. So although you can't gauge the porosity very well in a photomicrograph, our gas permeability tester allows us to see that nothing's getting through this coating. It's actually quite tight. Here we have an example of the difference of coatings applied by our standard AK07 standard HVAF coating, and the same material applied by our convertible gun, the C7, with added oxygen. And you can look at this, and yeah, there's aluminum oxide in there, same amount in both, but clearly the C gun is creating more oxidation, and that's because there's more oxygen involved. Not as much in a pure HVOF coating, but more than in a pure HVAF coating. So clearly the AF coating is more desirable if you can use it, and the AF coating is necessary when you have to meet an AF spec. And the good news is our OF coating is going to be better in any number of ways than a pure HVOF coating. Reason being, we're not running 100% oxygen, we're only increasing it a little bit. Here we have a soft coating example. This is aluminum sprayed with no grit, and you know, it's a respectable coating as aluminum goes, nothing really terrible. But with grit, again, a lot more is retained in the coating, clearly metal matrix. It's impossible to tell what the porosity is because of the aluminum oxide. But once again, our gas permeability tester allows us to see that this coating is superior to this coating. Amazing. Who would have thought? And this is a really good one. This is the coating that we sprayed in testing for those vessels we sprayed for Chevron. Here's the coating in its unaffected state as sprayed with the aluminum oxide. And here it is after it's been subjected to boiling sulfuric acid. I forget how long the test went, but it was a while. Oh yeah, right here, 2 weeks. 2 weeks, and you know, nothing happened to the coating. It looks, you know, just as good as the day it was prepared. Here's another example, same thing. This is a night crowley with aluminum oxide, and they're both at 200 magnification. The one on the right, no aluminum oxide, and even though the one on the left looks worse in testing, it turns out to be a much better coating. Gas permeability testing, hardness, ductility, K1C, all of that stuff, much better over with the aluminum oxide in it. And some of the advantages that arise from using the HVAF process or our reduced oxygen HVOF process is that we have almost no oxidation of the feedstock material. Coatings we produce, almost everything we spray is gas tight. We have high throughput, as I said, carbide's up to 60 pounds an hour. Actually, it's a little higher than that. Metal's up to 50, and deposit rates, deposit per pass between 1 and 2 thousandths per pass, and that's even for carbide. So, you know, comparing that to an OF carbide, a plasma where you're putting down 1/4 to 1/2 mil per pass, we're putting down 4 times as much, 4 to 5 times as much material in each pass. So any job is going to take fewer passes. You're putting less heat into the part. You're watching it cool off for less time. It's much more efficient. And we're not even integrating blasting with HVAF, which is a whole other discussion that saves a ton of time and money in preparing the part for the coating. We have no nozzle clogging whatsoever for virtually everything we spray. There's a couple problematic materials, but that's cleaned up by adding grit. And the key applications we've been involved in here at the headquarters spray shop, which is really our R&D lab, we do a lot of hard chrome replacement, especially for hydraulic rods in marine environments where corrosion is a problem because you know, everybody knows hard chrome plate is porous. We also do very well with corrosion resistant at elevated temperatures with chrome carbide and other materials like that. And we can provide extraordinarily high wear resistance at an extremely low cost. Mostly because of the quality of our coating created, we can use a much thinner coating than in traditional thermal spray. So in traditional thermal spray, where you might need 10 or 20 thousandths of a coating, we can get away with 5 to 8. So we're even using less material, further increasing the efficiency of the process. And wherever you are, we have a distributor that can help you. China, Italy, Poland, India, Japan, Korea, Russia, Southeast Asia, and on the East Coast we have Cloud Houses and Systems. We're available to help you at any time should you have any question or need any further information. My email address is here, and our website is here. Thank you so much for listening to our webinar. Hope you come back and see us for the next one. Be well. Bye-bye.